Okay, welcome back. We're in the midst of trying to pinpoint the location of a star on the celestial sphere. And what we left off with last time was the concept of declination. We can look at a star, in this case this star, and we can specify how far north or south this star is of the celestial equator. Again, the celestial equator has a value of 0 degrees declination. The north celestial pole has positive 90. South celestial pole has negative 90 degrees declination. So in this case, this star is 29.5 degrees above the celestial equator, or we would say positive 29.5 degrees declination. But the problem is, just by giving that value does not pinpoint this particular star, because we could choose any star along this gray line, this gray circle, and that would, all those stars would have the same declination value. They'd all be the same distance above the celestial equator. We need some more information. We need another coordinate, and that coordinate is what's called right ascension. Right ascension comes from something called the ecliptic. The ecliptic is the path of the sun through the sky during the course of the year. And I'm going to explain more of this when I give you some background on the celestial sphere. But suffice it to say that all the stars in the celestial sphere don't move. They're so far away that we consider them to be fixed. And therefore, once we define the coordinates for a particular star, those don't change. However, the sun and the planets, because they're so close, they don't just stay in the same space, the same place all year. They appear to move. That's largely because either in the case of the planets are moving, or in the case of the sun, it appears to move because the Earth is moving as well. It's orbiting. It orbits the sun, and therefore the sun appears to take different locations over the course of weeks or months with respect to the background stars. And so it traces out a path called the ecliptic during the course of the year. So we define right ascension as being, well, first of all, this ecliptic, notice that sometimes it's above the celestial equator, sometimes the purple line is above the green line, sometimes the purple line is below the green line, and sometimes the purple line intersects the green line. Where they intersect, that's what's called the equinox. And in this case, this is the vernal equinox. I'm going to put on this equinox right here is where the sun is on March 21st. The sun is essentially over the equator on March 21st. In late September, the sun, remember the path of the sun during the course of the year is the purple line. It's over the celestial equator on September 21st. It's well above the well above the celestial equator at the summer solstice, and it's well below the celestial equator at the winter solstice. And so we define right ascension as being zero hours right ascension as being where the ecliptic intersects intersects the celestial equator when the sun is going from south to north. Okay, so this is essentially in the spring, vernal equinox. And then we count right ascension going eastward from that 0 point. So if I'm going to move my star. I'll leave it at essentially the same declination, it was 29.5 or thereabouts. But now notice that I've moved it over here. So in this case, I'm going to take off some of these labels so as to not confuse you. So notice now, this particular star is a certain distance east of this intersection. So it's a certain distance from the vernal equinox. And we, instead of giving it in degrees, we give it in hours. So in right ascension, it's defined in hours. And that's because the Earth spins once on its axis in 24 hours. So we give right ascension in hours. So in this case, it is 4.3 hours is the right ascension value. I think I can move my star all the way over to the fall equinox. And notice the right ascension value, the one in blue, keeps on increasing. It goes up. Now I'm at 12 hours because I'm halfway around from the vernal equinox. I can continue around. Notice the right ascension value continues to climb, 16.4, 19.9, until eventually I get up to almost 24 hours right ascension. Again, this specifies now how far around the celestial sphere I am. So again, declination, the one in red, is how far north or south you are of the celestial equator. The blue value, the right ascension, tells you how far east you are of the vernal equinox. And once I have those two values, I can specify the location of any particular star. So this star is 40.1 degrees declination and 2.0 hours right ascension. Those are the coordinates for that particular star. Now let me go back into the Sky Map Explorer to show you what you'll be looking at. Because again, you're supposed to figure out the coordinates of a couple of stars in the constellation Orion. So when you click on the Sky Map Explorer, you'll wind up with what I was just looking at, but in this case this is a nighttime view. So you're seeing the celestial sphere, you're seeing all the stars on the celestial sphere. And if you look carefully, close to the celestial equator, I'll show you, I'm going to click on, there's the celestial equator, you'll see that famous, very well-known pattern we call Orion. There's the belt of Orion, and then these are the two stars that are in question, Betelgeuse and Rigel. So if you click on Betelgeuse, you'll be given its declination value as well as its right ascension. And likewise with Rigel, you'll be given similar values. Notice that the declination is negative. That's very important. Negative declination values indicate that that star is south of the celestial equator. Okay, so that'll help you answer the next couple of questions in the student guide. Moving on into page 4. And you can answer this little table here, again playing around with that Sky Map Explorer. The seasons in the ecliptic, I encourage you to go through the orbits and light background material. And I'm going to go straight into, just to keep things short, I encourage you to check out the orbits and light thing, because one thing you'll notice is that because the sun does move on this ecliptic, the angle of the sunlight changes during the course of the year, and that's what we're going to deal with in the Seasons and Ecliptic Simulator. And so I'm going to just show you how to maybe do this first row in this table on this is page 7. They want to know the right ascension and declination of the sun on February 5th. So you go into your simulator and you choose that date. So you have to change the date to February 5th. And you can do that just by clicking and dragging on that timeline. So now notice February 5th. Okay. It's wintertime, right? At least winter for the northern hemisphere. We need to figure out what the right ascension and declination is of the star, of the sun. Well, notice that they give you that. Sun's declination, sun's right ascension. So you fill that information in. Notice that the declination is negative 15.8. The sun is, at that time of the year, it's below the celestial equator. And the sun's right ascension is 21.3 hours. Remember, the vernal equinox, where the sun starts each year, is 0 hours right ascension. And then during the course of the year, it moves eastward. So by the time you get to, if you start in March and you're in early February, yeah, you should have a value that's pretty close to 24 hours. Because it's almost completed its entire trip around the ecliptic at that point. Okay, a couple of other things we need to fill in for this chart. We need to come up with the latitude of most direct sunlight. So what you do is you go into your simulator, and you grab your little guy, and you drag him until, notice the sun's altitude. We want the sunlight to be coming straight down. We want very direct sunlight. So the latitude of that particular guy is about 16 degrees south. Which makes sense, because our light is coming in at about 16 degrees south of the celestial equator. So that's where the guy would have to be in order to have direct sunlight. Now they want the latitude of least direct sunlight. So as I move my guy, notice that the light is getting more and more angled, more and more angled, more and more angled, more and more angled, until essentially it disappears pretty close. So you get way up here, and that's what would be your latitude of least direct sunlight. And you fill in the information. Again, try it from a bunch of different times of the year. And then finally, you can kind of play around, go to these different latitudes, and see. So if I choose, they want me to go to 23.5. They want me to go to the Tropic of Cancer. So about here, 23 thereabouts. And then just go ahead and let the animation start and see what happens to the sun angle during the course of the year. Does it ever get directly overhead? How many times does that occur? And fill in that last little piece of information on the worksheet. Like I said, that helps you get through the student guide. I'm going to give you some more background information in a future video about these things like ecliptic, declination, right ascension.